Chapter 8, Module 4. We have seen earlier that on a simplicial complex, we can define orientation by introducing ordering of vertices. We have also constructed chain groups, chain complexes, and thereby a sequence of groups called simplicial homology groups on a simplicial complex K. Now, in this module, we shall see that the homology groups, the simplicial homology groups does not depend on the orientation of the given simplicial complex K. Let us recapitulate a few things which we require in this module. Suppose K is a finite oriented simplicial complex. The ordering of the vertices is given by A0 less A1 less A2 etc., up to less An, where A0, A1, An are the vertices of the simplicial complex K. Now, we consider the chain complex. Here CQ1 K, CQ K and CQ minus 1 K, these represent the simplicial chain groups which are described here, like CQK is isomorphic to the direct sum of the cyclic groups generated by the Q simplexes, and delta Q's are the boundary homomorphisms. Now, a working formula for delta Q is like this. When it is operating on a generator A0, A1, AQ, then the value is summation I equal to 0 to Q minus 1 to the power of I, the simplex A0 to AQ deleting the ith vertex AI. So, that means delta Q is operating on a generator A0, A1, AQ and ultimately give a Q minus 1 chain, that is a member of CQ minus 1 K. Here, as already mentioned, that the simplex A0 to AQ with AI cap in between implies that it is a K minus 1 simplex omitting the vertex AI cap from the Q simplex A0 to AQ. Now, the Qth simplicial homology groups are defined as HQK is equal to ZQK by BQK, that means the quotient group kernel delta Q by image delta Q plus 1, where Q is any integer between 0 and the dimension of K. Now, if we take Q to be less than 0 or greater than dimension of K, then HQK is defined as the trivial groups. Now, we first show by an example how to find the homology groups of a simplicial complex. Let us take this example. K is a simplicial complex consisting of 3 zero simplexes, that is A0, A1 and A2, and 3 one simplexes, that is A0, A1, A1, A2 and A0, A2. We shall show that the simplicial homology groups of K are given by HQK equal to Z when the value of Q is 0 or 1, otherwise it is trivial. Now, let us take a specific ordering of the vertices of K. The ordering is given as follows, that it is A0 less than A1 less than A2. So, K becomes an oriented simplicial complex. Since there are 3 0 simplexes and 3 1 simplexes, the non-trivial portion of the chain complex is this one. It is trivial group to C1k to C0k to trivial group, and we see that the only non-trivial boundary homomorphism is delta 1. Therefore, H1k as it is defined as Z1k by B1k, it is Z1k by trivial group which is isomorphic to Z1k. H0k is equal to C0k by B0k, and rest of the groups HQk are trivial. So, we need to compute Z1k and B0k, that means kernel of delta 1 and image of delta 1. Further, we know that C0k is actually the direct sum of 3 infinite cyclic groups generated by the vertices A0, A1 and A2, and C1k is the direct sum of the 3 infinite cyclic groups generated by the 1 simplexes A0, A1, A1, A2 and A0, A2. Now, let us take any point z from Z1k, then z being a member of C1k, it has the form M0 A0 A1 plus M1 A1 A2 plus M2 A0 A2, where M0, M1, M2 are any integers, and since it is a member of Z1k, delta 1 z is equal to 0. So, delta 1 operating on this particular element z gives the value 0, means applying the definition of boundary homomorphism, this M0 A0 A1 reduces to M0 A1 minus M0 A0, delta 1 M1 A1 A2 reduces to M1 A2 minus M1 A1, and delta 1 M2 A0 A2 reduces to M2 A2 minus M2 A0. So, the whole thing is equal to 0 implies this. That means, if we collect all the coefficients of A0, then we get the coefficient as minus M0 plus M2. If we collect all the coefficients of A1, then that is the integer M0 minus M1, and collecting the coefficients of A2, we get the integer M1 plus M2. So, the independence of the vertices gives us M0 equal to M1 equal to minus M2. So, that means, if we put these values of M0, M1 minus M2 in the expression of z, we get z is equal to M0 times some sigma, where sigma is the chain A0 A1 plus A1 A2 minus A0 A2. So, since it is a combination of 3 1 simplexes, this is an element of C1k. So, any element z belonging to Z1k is in the cyclic group generated by sigma, and as we know that there is only one infinite cyclic group, that is z up to isomorphism, we have Z1k isomorphic to Z. Now, we find what is B0k. So, let us take an element W from B0k, then there exists some Z from C1k such that W is equal to delta 1 Z. Now, this implies that there exists some Z which is having an expression of the form M0 A0 A1 plus M1 A1 A2 plus M2 A0 A2 such that W is equal to delta 1 of that expression, which implies W is equal to M0 A1 minus M0 A0 plus M1 A2 minus M1 A1 plus M2 A2 minus M2 A0, which implies W is equal to minus M0 M2 A0 plus M0 minus M1 A1 plus M1 plus M2 A2. So, W is of the form T0 A0 plus T1 A1 plus T2 A2, where T0, T1 and T2 are 3 integers with the property that they sum up to 0. So, we can rewrite W in terms of any 2 of these integers, eliminating the third one. So, we get W is equal to T1 times A1 minus A0 plus T2 times A2 minus A0 with these A1 minus A0 and A2 minus A0 belonging to C0k. So, in other words, W is a linear combination of 2 1 chains, and therefore, any W belonging to B0k is a member of the infinite cyclic group Z direct sum the infinite cyclic group Z. Now, we can see that the cyclic groups are actually generated by A1 minus A0 and A2 minus A0, but since there is only one infinite cyclic group up to isomorphism, we can very well replace the cyclic group generated by A1 minus A0 by the cyclic group of integers Z. And so, we can say that B0k is isomorphic to Z direct sum Z. Therefore, we finally get the expression for H0k as direct sum of 3 copies of Z quotient with direct sum of 2 copies of Z, so that it is isomorphic to the infinite cyclic group Z. And similarly, H1k is Z1k by B1k, which is Z quotient with the trivial group. So, that means it is isomorphic to the infinite cyclic group Z. So, as we mentioned earlier, any other homology group will be trivial in this case. So, ultimately we get HQk as Z when the value of q is 0 or 1 and trivial otherwise. In the last example, we have seen that we have started with a specific ordering on the simplicial complex K. Now, if we change the ordering of the vertices, instead of taking A0 less A1 less A2, if we start with say A1 less A0 less A2, then will it change the homology groups of the simplicial complex? The answer is no, it will not. We shall prove this, that if we change the ordering of vertices, thereby changing the orientation of the simplicial complex, we are going to get the same set of homology groups. Suppose K1 and K2 are two oriented simplicial complexes obtained from a simplicial complex K, then the homology groups HQK1 and the homology groups HQK2 are isomorphic for each Q. Now, let us prove this theorem. Suppose I start with some sigma q from K, it is a Q simplex. Then corresponding to that sigma q, let us denote by sigma q1 the oriented Q simplex in K1 and denote by sigma q2 the oriented Q simplex in K2. Then sigma q2 is either positive sigma q1 or negative sigma q1. These are the only two possibilities. Therefore, we can get a function phi from K to minus 1 1 such that sigma q2 is phi sigma q sigma q1, where phi sigma q is either plus 1 or minus 1. Now, we define a function f sharp from CQK1 to CQK2 by this formula. Let us look at this formula. If we take an element of CQK1, it is nothing but a chain of the form summation mi sigma q1I, where I varies over the number of Q simplexes present in K1. Now, that is equal to, when f sharp is operated on that particular element of CQK1, that will give us an element of the form summation mi phi sigma qi, that is just a number plus 1 or minus 1. So, ultimately mi phi sigma qi is nothing but an integer, and sigma q2i, these are the generators of CQK2. So, ultimately the right hand side expression is a chain in CQK2. So, we get a map f sharp from CQK1 to CQK2. We shall show that this map is a chain map. That means, for that to be a chain map, we require this diagram to be commutative. In other words, we have to show f sharp composed delta q k1 is equal to delta q k2 composed f sharp. Now, to prove the commutativity of that diagram, it is enough to show that this diagram commutes on the generators of CQK1. Now, let us choose an generator sigma q1 from CQK1. Let us see what happens if f sharp composed delta q k1 is operated on sigma q1. We simply apply delta q k1 on sigma q1 and get the expression within the bracket on the right side expression. So, that means f sharp is operating on summation incidence number sigma q1 sigma q minus 1 1, that is just an integer, multiplied with sigma q minus 1 1. Here sigma q minus 1 1 are the q minus 1 simplices running over k1. Now, this expression is equal to summation incidence number sigma q1 sigma q minus 1 1 phi of sigma q minus 1 multiplied with sigma q minus 1 2. But that is equal to, if we replace sigma q1 by phi sigma q2 and sigma q minus 1 1 by phi sigma q minus 1 sigma q minus 1 2, then we get this expression which is equal to phi sigma q. We can take this integer out, this is just a number plus 1 or minus 1, and we can also take the integer phi sigma q minus 1 out from the above expression, so that we get phi sigma q minus 1 whole square. We already know that phi sigma q minus 1 may have two values, either plus 1 or minus 1. So, its square is always a positive 1, and therefore, we have the simpler form that is equal to phi sigma q summation incidence number sigma q2 sigma q minus 1 2 multiplied with sigma q minus 1 2. Now, the expression in the summation, within the summation, is actually delta q k2 of sigma q2, and since delta q k2 is a boundary homomorphism, by the property of homomorphism we can take phi sigma q inside. So, finally, we get delta q k2 of f sharp of sigma 1 q. So, that means f sharp becomes a chain map. In what follows, we shall see that a chain map induces a homomorphism between the homology groups. Now, in the previous theorem what we were discussing, that f sharp is a chain map, and therefore, it will give rise to a homomorphism between the corresponding homology groups. Now, there is no choice of k1 and k2. That means, we have defined f sharp from CQ k1 to CQ k2. We could have defined a function g sharp from CQ k2 to CQ k1, and we could have shown that g sharp is also a chain map. Thereby, we will get a sequence of homomorphisms between the corresponding homology groups. Now, it is not hard to see that these two functions, the homomorphism, let us call it f star from HQ k1 to HQ k2, and the homomorphism g star from HQ k2 to HQ k1, they are inverse of each other. So, that means f star and g star are actually isomorphisms. So, that will establish the theorem that HQ k1 and HQ k2 are isomorphic. Now, let us show that for any simplicial function f from any simplicial complex k to another simplicial complex L give rise to induced homomorphisms between HQK and HQL for every q. So, we recall the definition of simplicial map first, that if K and L are two simplicial complexes with the set of vertices of K as V R K and set of vertices of L as V R L, then a map is called a simplicial map from the set of vertices of K to vertices of L, defined as follows. Now, loosely speaking, a simplicial map carries a simplex of K to a simplex of L. So, in what follows, K and L will denote simplicial complexes without further mention. Now, we define for any simplicial map F from K to L, a map F sharp from CQK to CQL given this way, that whenever V0, V1, Vq is a Q simplex such that the function f takes the vertices fv0, fv1, fvq to distinct points, that means the vertices fvi's are all distinct in L, then f sharp operated on the Q simplex V0 to Vq is the simplex fv0 to fvq. But if fvi's are not all distinct, then the value is assigned as 0, that means the trivial element of CQL. So, the definition of f sharp takes the form by applying additivity. Now, if I take Q to be less than 0 or Q to be greater than dimension of K, then f sharp is defined as the 0 map. Now, if you take the collection of all such functions f sharps, then this collection is called a chain map induced by the simplicial map F. Now, if F is a simplicial map, then it can be shown that f sharp composed delta q k is equal to delta q l composed f sharp, or in other words, the diagram shown here will commute. Now, as a corollary to this theorem, one can establish that f sharp will take all the q cycles of K to the q cycles of L, and f sharp will take all the q boundaries of K to the q boundaries of L. So, let us try to prove this corollary, that if we take Z from ZQK, then Z has the value 0 under the map delta. That means, f sharp composed delta on Z is equal to 0, so that we have delta of f sharp Z is equal to 0, that is f sharp Z is in ZQL. Now, if we take B from BQK, then there exists some A in CQ plus 1 K such that delta A is equal to B. So, f sharp of delta A is equal to f sharp of B, which is delta of f sharp of A equal to f sharp of B, and that means f sharp of B is in BQL. So, from there we define a map F star from HQK to HQL given by f star Z plus BQK is equal to f sharp Z plus BQL. This is well defined because of the first part of the corollary, that Z1 plus BQK is equal to Z2 plus BQK, which implies Z1 minus Z2 is in BQK, So, that means f sharp operated on Z 1 minus Z 2 is in BQL, and therefore, f sharp Z 1 plus BQL is equal to f sharp Z 2 plus BQL. Also, f star is a homomorphism, and that follows also from the corollary that f star on two elements of HQK, one is Z1 BQK, the other one is Z2 BQK. So, f star operated on the sum of these two elements give us f star Z1 plus Z2 plus BQK, which is f sharp Z1 plus Z2 plus BQL, and that is equal to f sharp Z1 plus BQL plus f sharp Z2 plus BQL. So, we get f star from HQK to HQL corresponding to a simplicial map f from K to L given by this expression in terms of the chain map. This f star is called an induced homomorphism. We can show that this induced homomorphism has the functorial properties. That means, if f and g are two functions in simplicial complexes, that is they are the simplicial maps, then corresponding to them we can have f sharp and g sharp between the chain complexes. The diagram for the chain complexes, that is CQK to CQL and a map from CQL to CQM, this diagram will commute once we know that a similar diagram, that is from K to L and L to M, the functions, the composite of the functions f and g, that diagram commutes. And secondly, if identity is the simplicial map from K to K, then I sharp, the induced homomorphism from CQK to CQK, is also the identity homomorphism. Now, to prove these functorial properties, it is enough to prove for the generators. So, we start with a generator sigma is equal to V0 to Vq, a Q simplex from CQK, and we see what happens to the diagrams G composed F sharp operating on sigma and what happens to G sharp composed F sharp operating on sigma. So, there are three possible options. The first case is when all these f v0 to f vq are not distinct. So, if they are not distinct, then G of f v0 to G of f vq, they are all not distinct. And so, if we see what is G composed F sharp sigma, we will see that that is 0. On the other hand, if we compute J sharp composed F sharp on sigma, then that will again give the value 0. In case 2, let us assume that all f v0 to f vq are distinct, but G of f v0 to G of f vq are not distinct. Now, since they are not distinct, of course, we have G composed f v0 to G composed f vq are all not distinct. So, G composed f sharp on sigma is equal to 0, but G sharp composed F sharp operating on sigma is G sharp operating on F V 0 to F V q. Now, since F V 0 to G F V q are not all distinct, we have G sharp operating on F V 0 to F V q is equal to 0. Now, in case 3, we assume that F V 0 to F V q and G F V 0 to G F V q are distinct. So, all these G composed F V 0 to G composed F V q are distinct. So, G composed F sharp sigma is equal to the simplex G composed F V 0 to G composed F V q, which is equal to G sharp on the simplex F V 0 to F V q, and that is equal to G sharp composed F sharp of sigma. Hence, G composed F sharp is equal to G sharp composed F sharp. Now, similarly, for the other case, if we start with I sharp operating on sigma, then that is equal to the simplex I V 0 to I V q, which is equal to simplex V 0 to V q, because I is the identity function, and that is equal to sigma. So, that means I sharp is again an identity function. Now, as a corollary to this result, we get that F star, the induced homomorphism, also possess the functorial properties, and from those functorial properties we can use the language of categories and say that if we start with a category of simplicial complexes and simplicial maps and call that category S, and if we start with an abelian group category, that is the category of abelian groups and homomorphisms, then for each integer q, H q will take the objects of S to the objects of AB and the morphisms of S to the morphisms of AB, so that it has the functorial properties, thereby giving H q as a covariant functor. In this chapter, we have seen how to construct homology groups for a class of topological spaces. There are certain limitations for constructing simplicial homology groups, because it cannot be assigned to any topological space. For constructing simplicial homology groups, we need to have a simplicial structure, rather a topological space must be a triangulable space. In the subsequent chapters, we shall see that for any topological space X, we can construct a generalization of such homology groups called singular homology groups. With this, we end chapter 8, module 4 as well as chapter 8.